In this problem, we're looking at a cube that has an elastic modulus and a Poisson ratio, and there are forces being applied to the different faces of this cube in normal directions. And the question is asking us, how much change in length is there going to be in the z direction for this particular cube? So let's go ahead and take a look how we can break the problem down into a framework that focuses on equilibrium and geometric compatibility and constitutive relationships. So we're following the framework given by Crandall, Dahl, and Lardner. Here we start with our humble cube. And we know that we have force in the x direction, and we have a force in the y direction, and we also have a force in the z direction. Now I've drawn them all coming out of the faces of the cube, and so that these would be in tension. You notice that one of these forces in the z direction is actually a negative value. Right, so that one will be putting the cube in compression in the z direction. But right now, for the sake of kind of consistency and nomenclature, we're just going to have all these forces coming out of the faces of the cubes. For the geometric compatibility, we can think of, again, this cube and then some type of change in geometry. And now there are normal forces here, no shear forces, so we're not really going to see a deformation in the shape, but we will see a potential change, right, in its overall dimensions. And it might be helpful in this case, maybe foreshadowing slightly, that we think in terms of general uh, uh, terms, okay? There's a Poisson ratio, which is going to be, the Poisson's ratio is going to dictate how stretching in one direction is going to lead to contraction in the other two directions, orthogonal directions. So this is kind of just an arbitrary, we're applying some forces and we're seeing some type of change in the x, y, z dimensions. Now, for the calculation of the stress involved with these forces, we have to think about the cross-sectional area of each of the faces. And it's a cube, and we've been told that the edge length is 12 centimeters. So each one of these faces is going to have the same area, and it's going to be given by essentially 144 centimeters squared. The sigma x will be the fx direction over that area, sigma y similar, sigma z similar as well. What about an appropriate constitutive relationship? Well, here we go. We can write epsilon x, epsilon y in terms of these normal stresses and the Poisson ratio and elastic modulus. So I haven't read them all out here, but this is the one that's going to be of concern to us because we're interested in seeing what the change in length in the z direction might be. Well, let's go ahead and define a dimension z. So this, I mean, it may be not the best choice. Maybe I should have done like L sub z or something, but I'm just going to say that this initial or this, yeah, this height, and that maybe that's not the best either because I'm kind of thinking, oh, is it this height that's initial or is this height? I guess now I'm thinking, okay, maybe this I could transfer to this, but it's just not drawn very well. But this is going to be the initial height, z. And epsilon z is going to be, or the strain in the z direction, right, is going to be delta z divided by z. So if I'm interested in delta z, the change in length in the z direction, we can rearrange things and just do z times epsilon z. And that's what we write out here. Okay, and so that's how we're going to go about solving this problem. Let's go ahead and put in some numbers for that. And we can start with Google. That's a fine way to go, I guess. Just have to keep track of things. See, as we get to these problems where there are more and more numbers and you have to repeat them in different spots, with Google is great, but sometimes it's better to do a little bit of code. Okay, so we have a z over e. So the original z, okay, was 12 centimeters. So we're going to do 12 centimeters. Okay, and we're going to divide that. Maybe I'll put these in parentheses just to be extra clear in terms of how things. Divide that by the elastic modulus, which is 206 gigapascals, like that. Then we're going to multiply, and we have some more parentheses we are going to employ. So we have an FZ, okay, that's the -9 kilonewtons. All right, so we have an idea that's probably going to be negative. Do you see that? Because this quantity is going to be negative, the FZ is, and then Fx and Fy were both positive, and we have a minus that, so we're going to have a negative Z in the end. All right, so -9, and we're going to say kilonewtons. So 9 minus 9, and I'll say kilonewtons, divided by, and maybe I should put this in, I should put this one in parentheses as well, divided by the cross-sectional area. So we're going to have to repeat this. Well, no, I don't have to. I know it's 144 centimeters squared. Okay. And then I'm going to do minus, and my nu is 0.28. Okay, times, I've got, again, a force, so this is going to be 11 kilonewtons divided by the cross-sectional area, which again is 144 centimeters squared. Okay, and then I'm going to do plus, this is Fy, this is 21 kilonewtons divided by 144 centimeters squared. All right, and then I gotta close the parentheses appropriately. So let's see here. I think this, yep, I got one more that, because this one right now balances with that one. See, it's just such a pain to do this. And I don't even know if it's gonna work out. Let's see what happens. If we look at the answer, well, okay, it gave me an answer in nanometers. So let's see how Python turns out with trying to do the same calculation. So for that, we'll come over here. We'll go ahead and create a new Colab notebook, and we'll import NumPy as NP, Control Enter. Knows I want to do another one. I guess it's learned. Okay, so I've got a Z, which is going to be equal to 12 centimeters. So I'll do 12e to the minus 2. That gives it in meters. I've got a elastic modulus, which was, I think, 206 gigapascal, so E9, and that will be in pascals. We've got Fx, we'll just go ahead and maybe do them all. Fx was, what was the value? Fx is going to be 11 kilonewtons, so 11 E3, and that will be in newtons. Fy is going to be 21 E3, and that will be newtons. Fz is minus 9, okay. E3, sorry, and then that's newtons. Okay, what am I forgetting? We have, well, we could do this. We can say that the area is going to be z squared. Okay, that's good. So that's going to give us units of meters squared, actually. All right. Oh, a nu. We had to put in a nu. Nu was like 0.28, I think. Is that right? Yeah, 0.28. Okay, and that's just Poisson's ratio. This is dimensionless. We know that. So let's see. Okay, so the delta z is going to be equal to z divided by e times this quantity fz over a minus nu times quantity fx over a plus fy divided by, well, even knows. And it's showing me nicely where how the parentheses line up. I think that's good. So we're going to print delta z, and that's going to be equal to NP round. Okay, and so we have delta z here. They wanted the answer in nanometers, so we'll go to 1e9. Okay, and we'll do 1 of that, 1 decimal. Actually, you can't see that. Okay, now you can see it. I was typing, I guess, blindly into the dark, and we'll do nanometers like that. All right, I think that should work. Let's see what we get. Little suspense, pull it down, minus 727 nanometers. And what do we get when we do it over here? Minus 727 nanometers. Awesome. Okay, so I hope you find this example helpful. It's a demonstration of how the Poisson ratio uh, interacts with stresses in orthogonal directions to the direction that we're interested in analyzing, so the z direction. And using this constitutive relationship, we can figure out what the strain is, and then if we know what the initial length is, we can figure out what the change in the length would be. Thank you.